Okay, I'm back and I'm about to start with chapter 8, searching and sorting arrays. We're searching and sorting algorithms as well, because this chapter speaks about algorithms. What is an algorithm? It's a set of specific instructions in a specific order that resolve or perform a specific task. In specific, search algorithms. What is a search algorithm? A search algorithm is a method to locate a specific item in a larger collection of data. And this section in the book discusses two algorithms for searching the content of an array. It discusses linear search and binary search. Linear search is simply sequential search. So if I have my array, let's say this is my array, it has some items, and I need to find a specific item. Let's say I'm looking for the item or the value 2 on my array. These are 1, 3, 6, 2, 4, 3, 8, 7, 5, 9. Linear search is simply also known as sequential search, uses a loop to sequentially iterate or step through the array, starting with the first item. So linear means straight line, like this, from the beginning to the end, linear, sequential. So it starts, I'm looking for the value number 2. I want to know where is value number 2, which position, which index. So the algorithm starts from the beginning. Hey, item number 1, the first item, are you number 2? No, okay, go to the next item. Hey, are you number 2? No, okay, go to the next item. Are you number 2? No, okay, go to the next item. Are you number 2? Yes, okay, then report 3, which is the position. I found the value number 3 linearly. I found the value number 2 linearly or sequentially, and I found it on position number 3. So this is simply put, this is a linear search. Anytime you iterate from the beginning till the end in a sequential fashion, in a continuous fashion, in a linear fashion, that's a sequential or a linear search. Of course, once you find the position or find the item you're looking for or the algorithm is looking for, you don't need to continue. So the maximum number of comparisons that you could do is n, whatever the size. In case the value you're looking for is in the last position, then you're gonna do n comparisons, all the size. That's the worst case scenario. The best case scenario is having the item you're looking for at the very beginning. Then your algorithm has to do only one comparison. In case it's somewhere in the middle, then it's gonna find n log n or less than n times of comparisons, find the item, the specific item we're looking for, and then break. It doesn't need to continue. So worst case scenario is n comparisons. Best case scenario is one comparison, and then the rest is log n. So you're gonna have a loop, something like this. Let's say I have an array. My array equals 1, 2, or what did we have here? 1, 3, 6, 2, 4, 3, 8, 7, 5, 9. And then the target, my target, the specific item I'm looking for the item number 2. Let's say, so 2, 4, 6, 8, 10. So this is 10. Then I have a function, for example, called linear search. This method takes an array, takes the size of the array, and takes the target we are looking for. So this method returns the position. Where did we find where is the target located. So cout display the position. Now prototype, this returns a position. The position is an int. There is no decimal in the position, so the return type is a integer. The name is this. It takes an array of integers. It takes another integer for the size, and it takes a third integer for the target. Then I go and define it. I say, here is the return type. Here is the return type. Linear search, it takes int a array, int a size, int a target. In my case, I can start by saying, okay, I'm starting from result or position, we can call it. I'm starting from -1, right? If it's not found, I'm gonna return -1, means it's not found. If I start from 0 and I don't find the item, then I'm gonna have to return 0, which can be confusing. Hey, is 0 means, does 0 mean found or found on position number 0 or found or not found at all? So I'm gonna start by saying it's -1. In case I find it, I set the value to result. In case I don't find it, then I just return result. So L result. Here I'm gonna try in this, between these two lines, I'm gonna try to find it. If I find it, then I'm gonna invoke result. I'm gonna change the value of result. In case I don't find it, I do nothing, then result will be returned as -1. Then I'm gonna have a way to keep track of my index. So I'm gonna call it index I. You can call it I. So L index. I'm gonna keep it started from 1. Then I'm gonna say it's not found. Bool. So I'm starting by saying not found, right? The same initialization logic I'm gonna use for this Boolean. My initialization is pessimistic, not found, and the result is -1, so false. Now I attempt to find. In case I find it, then I say, okay, found is true and result is whatever the result is. So I'm gonna say, while, what are my cases? While I still, if I bring back, in case I wanna go linearly and find that item, what are my cases? My break conditions would be, I either reach the end, no more data, or I found what I'm looking for. In other words, if I'm starting from here and iterating, in what conditions do I stop? There are only two conditions. I either found the item, then I stop, or I'm looking for the item and I reach the end. So I have the size, right? Meaning, while my index is less than size. While this is the condition and it's not found yet. If this condition is true, if I am still within the size, but I found it, I still need to break. So both these conditions need to be true in order to break. I didn't find it yet, and there are still more to go. So while if this confuses you, we can do it like this. While found is false, and while index is size is less than size, keep going. While I'm going, I'm gonna check, I'm gonna do the comparison. If a array at my index, at the position I'm on, is the target I'm looking for, if that's the case, then set result. So set result is at this index. index. And found is true. This way I break out of the loop. Done, found. Oh, and in case this is not the target, so if this is the target, do this, and found will break out of the loop. If this is not the case, then I'm gonna say just move to the next one. Move to the next one. In case I didn't find it, and this is the last index, then this will fail, then the entire statement will evaluate to false, and it will break out, it will return result. So I'm looking for 2. 2 is in 0, 1, 2, 3. Then this line should return 3. Here it is, 3. If we want to step through the code, stepping into a array is some data. Memory address starts from here. And the first item is 1. I cannot see the rest of it because at this point, it's just treated as one beginning address. The compiler in this scope doesn't know the end, but in this scope knows the end because it was declared right here. So I have a beginning address, I have a size, and I'm looking for 2. Okay, starting from not found, the mentality of not found. Index is beginning, mentality is not found. While this is true and this is true, both need to be true in order to enter. Is index less than size? Yes, index is 0 and size is 10. Did we find it yet? No, we didn't find it. Okay, so both of them is true. Enter. Hey, at this index, at 0, is this our target? No, it's the number 1. Okay, then move. Is this the target now? No. Okay, then move. Is this target now? No, then move. So now it is the target. Hey, at this target, at this position, is this the target? Yes. Okay, cool. Then this is where we found it. We found it at index number 3. And we trigger breaking out of the loop. Hey, found, you're now true. Okay, move to next. Hey, did we find it? Yes. Okay, this will evaluate to false. This is still true, but false and true, the entire statement will evaluate to false. Remember, with the logical and, both of them need to be true. Return result 3, display result, boom. So that was linear search. Linear search is inefficient. But what's good about linear search is it's straightforward. I look in the code, I understand right away what it's doing. It's clear, it's simple. You know, it's the simplest method that you could do for searching for an item. One by one, right? You go from the beginning to the end. Hey, are you what I'm looking for? No. Okay, are you? So it's very simple. But it's inefficient. It's inefficient because of the different scenarios that you have. If you have right now, we have a simple example, 10 items. But what if you have a million items? Imagine you have a million items, and every time you need to find a specific item, then you have to iterate. You have to iterate 1 million item, right? Because the average is having the item in the middle at 500,000 and position 500,000. So that's the average. Every time you're trying to search for an item, the average is 500,000 comparisons. So it's inefficient. The book tries to say that in this section, and then it introduces a new search, which is binary search. So it's a linear search is, the advantage of the linear search is its simplicity. It's very easy to understand and implement. Furthermore, it doesn't require the data in the array to be stored in any particular order. So the order doesn't matter. Whatever the order is, I can start linear searching. However, the disadvantage is it's inefficient. If the array being searched contains 20,000 items, the algorithm will have to look at all 20,000 elements in order to find a value stored in the last element. So if what I'm looking for is 9, I have to iterate number of size times. Whatever the size is, iterations equals to iterations. Then it introduces binary search. So binary search is an algorithm. It's a smarter algorithm, kinda. It's a clever algorithm that is much more efficient than a linear search. The only requirement for a binary search is to have the data sorted. The data must be sorted before starting binary search. It's called binary because by two. Linear search starts from the beginning all the way to the end. Binary search starts from the middle. And the fact that values would be sorted for example, 1, 2, 3, 4. We had 6, now 7, 8. We no longer need 7, we need 9, and we had maybe 2 sevens. So 7, 8, 9, 2, 4, 6, 8, 10. So let's say 2 threes, 6, 6, 7, 7, 8, 9. So if they are sorted, I start from the middle. What is my target that I'm trying to find? 2. I start in the middle. Hey, is 2 less than 6 or greater than 6? The fact that the array is sorted and the fact that 2 is less than 6, I immediately eliminated half of the data right away. Boom. I no longer need to look right because I know that my target is less than 6. So now that I eliminated half, then my focus would be on these items. I also repeat, I look in the at the middle. Hey, is 2 less than you? Hey, item in the middle. Is my target less than you? Yes, it is less. Okay, then I eliminated half of my data. Then again, to the middle. Hey, 1, is it greater than? Usually when you are even and you go to the middle, you grab the left one. So hey, 1, is my target greater than or less than? Well, it's greater than. Okay, then move away from me. I don't need to look to the left portion, at the left portion. Come on. I just need this, yep. Since I no longer have a middle and the size is 1, then I found it. This is the position. So it only took me 2 comparisons out of 10 items. I only did 2 comparisons in order to find my item. However, in case of the linear earlier, when the data wasn't in a particular order, it took me 4 comparisons to find 2. So binary search, although it requires data to be sorted, but it's very efficient in this way. It eliminates half of the data right away. If you want to see an example, so let's call this binary search. And this binary search will take an array size and the target same, and it will return the position. Yep. So function blah. I know. Blah blah blah. Go here. Go here. Get back. Get back. Get back. So here is my array. It's sorted, and I'm looking for 6. 6 is at 0, 1, 2, 3, 4. So now I go to my focus. I'm a worker function now. Same case, I'm gonna say I need a position, which is like the result, L result. Being pessimistic, I didn't find it. I also need the bool, L found. I didn't find it. Starting from not finding it, returning result. So if the task in between fails, I'm returning -1, means it's not found. Then we need our boundaries. Remember how we start in the middle? How did I know this is the middle? Because I had boundaries. The very first time I started, my boundaries were, sorry, check. Okay. Sorry, back. So how did I know the middle? I knew the middle because the fact that I had boundaries. At the beginning, my boundaries were 0 and n-1. Is that right? The first item is at 0 and n-1, which is size -1, is the last item. So that was my boundaries. So I have an int called first item, and first item is at 0 at the beginning. Then I have last item, and last item is at index a size -1. Then I'm gonna do similar loop while it's not found yet, and while first is less than or equal last. So while I still have a group of data, once first becomes above last, I should stop. There is no way, there is no way, there is no point of continuing, because you're gonna see that first and found, first and last will be modified throughout this. The boundaries are gonna change every time I splice or slice half of the data. Last will move to the left, and first, in case I eliminate left section, then first is gonna move to the right. So as long as first and last are in this condition, first is before last, because if in case I have first and then last has been moved to the left of first, then I should stop. This was the end of the data. So while these are my cases, I'm gonna say, okay, the middle position. What is the middle position? Let's create a middle. Right now, middle is, I can start it here by saying it is L first. So it is it's a size -1 over 2. So I can say it is L first plus L second, if I want to be systematic. L first plus L second over 2. Yeah, yep. L last, sorry. Boom. This is middle. As a matter of fact, I could have just declared it here and then initialized it, not initialize it, set its value on each iteration. On each iteration, this is my middle. So on each iteration, every time I enter this loop, my middle would be the middle of the boundaries. Then I'm gonna say, okay, if my array, a array, at this position is the value, is what I'm looking for, a target, then I found it, right? Anytime it's equal to the target, then I found it. So L found equals true, then L result is whatever middle is. If this is the position we found it on, then this is it. And the fact that I invoked this variable, then the while loop is gonna break. I don't need to break. I don't need to explicitly say break. So if that's not the case, then I wanna check, is my target left of middle or right of middle? So if a array at middle is greater than target, a target argument. If this is the case, then move last, eliminate all the left section, right? Let's say this is middle. What's a good, yeah, this. Let's say I'm here. Then I'm checking. It's, well, sorry, it should be sorted, but you get the idea. So I'm checking. Hey, are you what I'm looking for? Oh, you're not what I'm looking for. Okay, is my target 2, the one I'm looking for 2, are you greater or less than 2? Then it's gonna say, in case it said it's greater than, then I wanna eliminate all the left section. So if this was first and this was last, and what I'm looking for is less than this, then I move last all the way here. Then this would be my new boundary. You see? So I'm gonna say L last is equal to middle minus 1. I don't want middle because I already checked middle. I just checked middle when I did this. So I don't need to check it again. Just skip it. So skip middle and everything to the right. Yep. And the opposite case is if A array at this position, we are still dealing with this position. On each iteration, we are dealing with this position. Hey, is it equal? Is it greater? Is it less than? So is it less than target? If it is less than target, then move first. L first equals L middle plus 1. Right? Here I eliminated all the right section. Here I'm eliminating the left section, means everything right to the middle. So plus 1. Save, return. Yep, so I'm done. Let me see out. So see out binary search, give it L array, L my array, give it 10 because that's the size, and give it my target. And it will display, what are we looking for? 6, and it will display 0, 1, 2, 3, 4. Here you go, found it. And it found it in 3 comparisons, in 2 actually comparisons, better than linear search. So this is very fast, we agree. This has less steps than linear search in order to approach the solution, but it needs a requirement, and the requirement is it has to be sorted. The fact that it needs to be sorted, then the book introduces sorting algorithms. Sorting algorithms are very important, and there is no best sorting algorithm. We can't say that the best algorithm is this algorithm, because it all depends on the situation. In some situations, some algorithms, sorting algorithms, are better than others. In different situations, different scenarios, different use cases, different or other algorithms are better. I always liked this video when I was a student. There was this visualize sorting algorithms. I don't know if you're gonna hear the sound. I don't know if Zoom needs me to allow it, but I don't know if you hear it. But if you don't hear it, just look up this, and it's gonna show you how different algorithms perform the task, and how different algorithms are faster than other algorithms. I don't know if you hear it, but every sound every tone you hear is a comparison, whether it's in the beginning, so different tones, right? Then it's starting from lower tones to higher tone. This would be the lower tone, this would be higher tone, to give you a sound effect on the way the algorithm is working. And the colors will indicate the number of comparisons. Then here, if you can see it, it says selection sort. And by the end, when it sorts all the data, imagine these are numbers, random data. So this would be, for example, the shortest one would be 1, the next one would be 2, 3, 4, 5, 6, all the way maybe 200. It depends how many spikes. So by the end, when this is done, it tells you it did 7875 comparisons, 15,500 array accesses, and 7.9 delay millisecond. So they reduced it, I guess, with some milliseconds for us to see it. Maybe I can change the speed, but you can do it yourself. So I'm gonna play some just so you can see how different algorithms just behave different. So for example, selection sort, if I slow it down, selection sort, let's say starting from this case, selection sort takes this value, let's say this value is 10, and then knows that 10 exists here. There is an index that keep track where is the green right now? We are here. Everything to the left is sorted. We are here. Let's say this index is 10. So it keeps track of 10. However, while it keeps track, it iterates the rest of the data, trying to find closest to 10. Then once it finds the closest to 10, it swaps it with the following item. So now it's 10, 11, and green then moves. We are now at 11. Then a new loop starts over. Okay, I'm at 11, I'm looking for 12. Once I find 12, I swap 12. So that's why it's called select. I select the closest and put it in its place. Then I iterate again, select the best one and put it back in place. Notice how did I say different algorithms are better in different situations. Notice with selection sort, the shorter the data or the smaller the data set is, the faster it is. Selection sort is very bad, well, worse than other algorithms on a large data set. Notice from the sound effect how it becomes very fast at the end. Once the data set is small, it becomes very fast. See how fast it was at the end? So it's good on small. This is insertion sort. Insertion sort basically starts from left. Well, most of them, or all of them, linearly start from left to right. Insertion iterates the entire data set. It grabs the lowest if we are sorting ascending. So it iterates all the data set. First iteration, which one is the minimum, finds the minimum, and then it inserts it to the left. Now that we have the first item, we go to the next item and iterate again. Find the minimum and then insert it. Then the third position. So it starts inserting value into positions repeatedly, I can say, or continuously. So here, notice again, when the data is bigger the data, the slower it becomes. Look how slow now. It grabs the value and tries to find the best spot. Oh, actually, yeah, insert. So it grabs the following. Yeah, true. So if with insertion sort again, sorry, my bad. Let's say it grabs green, or we are in green. It grabs this and takes it, insert it in the right position. Then it takes the next one, goes, insert it in the right position. Then takes the next one, insert it in the right position. This is how many comparison it's doing. Insertion sort. This is quick sort. It's called a quick sort. And look how it starts from last, from first, and moves to the middle. And it does this multiple times, multiple iteration, not just once. So it does it, then it does it again, then again, until everything is sorted out. See how fast it is for large data? And you can tell it follows divide and conquer, which is similar to binary search. It divides the data to sections and takes the middle and moves from right to the middle, from left to the middle. Once this is figured out, let's say, not sorted, it doesn't sort right away. Once this section is figured out, kind of reordered, it goes to the next section. See how it always breaks in the middle and then moves from left to right. Merge sort. Merge sort will sort them in pieces, also like a divide and conquer approach. It divides them, sorts them in pieces, then merges the parts. Merge sort, here it is. This uses a lot of memory because it copies the data to a different array. You know why it's copying? It's sorting, then back to the array. Notice, for example, now while it's going from from left to right, it's copying these values to a new array. So it's copying to a new array in a sorted order, right? And then it dumps them back. It puts them back in this array in a sorted behavior. So you can do this heap sort. Heap sort is very fast. So you can play with this as much as you want. Another one I need to show you is different when a data set is already ordered. You know, if a data set is partially sorted, also data size. Some algorithms are very fast on large data set and very slow in a small data set. The way they approach it creates more headache or more steps than needed. For example, for an array that is 5 items or 10 or 100 or even 1 million. In today's world, computers are fast. 1 million is still maybe less. It depends 1 million what. Let's say you are on Amazon. You might be saying right now, oh, well, what I'm looking at, this is very boring. But you will be surprised how important sorting algorithms are. For example, I go to Google and I say bicycle, right? Bicycle, 1, 2, 3, boom. How much did this take? 1 second or less than 1 second. About 1,080,000,000 results in less than 0.65 seconds. Not just that, Google didn't just grab 1 billion result and dump it in front of me. It also dumped it sorted by, if I start from the actual data, not the advertisements. This data is sorted by relevance, sorted by most related first, most relevant first, then less relevant, all the way to the last page. Then the last page would be the least relevant. Imagine you are on Amazon or eBay, and then I say, okay, I want bicycle. Now it's sorted as well by relevance. The first item is the most related to my search criteria. However, I can sort, and look how fast it is. I can sort by price from low to high. Boom. In less than a second, it sorted all the results up to 20 pages, maybe more. I can sort it again, sort it again. So so there is an algorithm that is sorting based on a criteria, and it has to do it very fast. Otherwise, customers wouldn't like Amazon, and they would say, "Oh, our website is so slow." So algorithms, sorting algorithms in particular, are very important, and it depends on the data set. It depends on whether it's partially sorted or not. For example, also, you see this low to high, high to low. If the user is on low to high and then switches to high to low, there is a specific sorting algorithm that is so fast in swapping the order, while other algorithms might be very slow in swapping the order. So the fact that we started from a sorted array, it's wise to pick a specific algorithm. So it depends, how are you starting? Are you starting with a sorted array? Are you starting with a partially sorted array? Are you starting with a million item, 10 items? So it depends on the situation. You pick the right algorithm. For this class, you're only responsible to know two sorting algorithms. One is bubble sort and one is selection sort. So I might ask you in the test, write a sorting algorithm or sort this array. You can pick whatever you want, bubble sort or selection sort. These are the two that you're responsible of. So back to the book. After binary search, they have explanation on why binary search is efficient. Then they have the program and the case study focus on software engineering. Excuse me, I need more water. Then we start with sorting algorithms. Sorting algorithms. And it starts explaining that many programming tasks require the data in an array to be sorted. Customer lists, for example, are commonly sorted in alphabetical order. Yep. Student grades might be sorted from highest to lowest. Product codes, etc., etc. To sort the data in an array, the programmer must use an appropriate sorting algorithm. A sorting algorithm is a technique for stepping through an array or a container and rearrange its content in some order. In some order, they didn't say ascending or descending, in some order, because it's based on the criteria of price or average customer review, etc., or feature, etc., etc. So some order. The result is in some order, particular to the business. Then they start with bubble sort. The bubble sort is an easy way to arrange data in ascending or descending order. It's called the bubble sort algorithm because as it makes passes through and compares the elements of the array, certain values bubble toward the end of the array with each pass. So bubble sort basically starts from here to here. It compares, hey, which one is bigger? The bigger goes to the right. The lower goes to the left. Then it compares these two. Which one is bigger? Come with me. Which one is bigger? Come with me. Which one is bigger? Come with me. Which one is bigger? Come with me until it reaches the end. On the first iteration, it's n comparisons. On the second iteration, it's n minus 1. On the third iteration, it's n minus 2. Because We no longer need to go up to n. We already put 9 in place. We already put 8 in place. Sorry, this is already sorted, but I'm trying to visualize it for you. I can do a Google one, or you can do it yourself. Say visualize bubble sort. So it's called bubble because on each iteration, the larger bubbles into the end. If I'm doing it in descending order, if I want to sort in descending order, then the lowest bubbles to the end. See the difference? If it's in ascending order, the larger bubbles to the end. If descending order, if I want to sort in descending order, then the lowest bubbles to the end. So it's bubbling anyway. Bubble sort. There's a complete code for how to do the bubble sort and explain exactly how it does it in figures, but I prefer visualizing a video. If you are like me, you don't like that, so visualize bubble sort. Bubble sort, here's bubble sort. See how when it started, it's comparing each two, and then the larger moves on. The larger moves to the end. The larger moves to the end. So this is bubble sort, ascending order. Then what else we have in the book? Of course, we have selection sort. Where is selection sort? So selection sort, my friends, selection sort keeps track of the index on each iteration. It's similar to a bubble sort, but on each iteration, it keeps track of the index. And instead of swapping every two together, it just swaps it with the end, with the last item. You see here, back to this. If I slow it down, notice in bubble sort, now, let's do the end, boom. Notice with bubble sort, it grabs an item, right? And then it compares these two. Then it compares these two. So it keeps swapping every item. However, with selection sort, it doesn't swap, it just compares and then swaps by the end. Instead of swapping throughout the iteration, it just swaps with the end. So it picks the larger, it keeps track of the larger, it doesn't swap. So the large stays in its place. It keeps track. Oh, okay, the largest so far is here. Let me compare without swapping. Let me compare. Oh, which one is the largest? This one's the largest. Okay, so now this is the largest. I keep track. Instead of swapping, I keep track. Then I compare with the next one. This is a small one with this one. Which one is larger? I'm still the larger. Okay, stay larger. Hey, which one is the larger? You're the larger. Okay, so now I keep track of this. I'm trying to draw an arrow. I'll keep track of this. So it keeps a track of the largest instead of swapping the largest. Bubble sort swaps. Swaps. You see how the large is moving? The large is moving until it reaches the end. Selection sort, nothing moves until the end. Once we reach the end, we kept a track of the largest. We swap this item here with the largest, and then we repeat. There are figures and there are codes. Let's see what else we have in the book before we call it for the day. Yeah, this is it, done. Review questions and exercises. So let me know if you have any questions, and good luck.